Right now, as you settle into these words, perhaps with a warm drink in your hands, feeling the heat transfer from the cup to your fingers, you're experiencing one of the universe's most fundamental rules. Heat flows from hot to cold. Always, without exception. It's so basic, so obvious, that questioning it seems absurd. Instead, but what if I told you that scientists have created systems where this rule breaks, where heat flows backward, where things can be colder than absolute zero, that ultimate limit where atoms stop moving entirely? Instead, this isn't science fiction or a mistaken measurement. It's real physics happening in laboratories right now. Systems at negative temperature on the Kelvin scale, not negative Celsius or Fahrenheit, where water freezes and we bundle up in winter coats, but negative absolute temperature, a realm that shouldn't exist according to everything we learned in school. Perhaps you're thinking this is impossible. After all, temperature measures the kinetic energy of particles. How can particles move less than not at all? How can something be colder than the complete absence of heat? Instead, the answer will take us on a journey through the looking glass of thermodynamics, where entropy runs backward, where adding energy makes things colder, and where the very concept of temperature reveals itself to be far stranger than we imagined. So adjust your mental thermometer, forget what you think you know about hot and cold, and prepare to explore a world where negative doesn't mean what you think it means, where absolute isn't actually absolute, and where the impossible is not only possible but useful. Temperature, as we experience it daily, seems straightforward. Things are hot or cold. Ice melts at 0 degrees Celsius. Water boils at 100 degrees Celsius. We measure fever at 37 degrees Celsius and set our ovens to 180 degrees Celsius. Instead, this is temperature, as humans have understood it for centuries, a measure of hotness or coldness that our bodies can feel. But what is temperature really? At its heart, temperature is about motion. The atoms and molecules that make up everything around us are constantly jiggling, vibrating, spinning, and colliding. The faster they move, the higher the temperature. The slower they move, the colder it feels. Instead, this understanding led to a profound realization: there must be a lowest possible temperature, a point where all atomic motion stops. This is absolute zero, 0 Kelvin, minus 273.15 degrees Celsius, minus 459.67 degrees Fahrenheit. It's not just very cold, it's the complete absence of thermal energy. You can't get colder than no motion at all, or so we thought. Lord Kelvin, who gave his name to this absolute temperature scale, declared in 1848 that this was the ultimate limit. It was impossible to go below absolute zero, because you can't have less than zero kinetic energy. It would be like having negative speed, nonsensical. For over a century, this stood as an unshakable law of physics. Absolute zero was absolute. The third law of thermodynamics even states that reaching absolute zero is impossible. You can approach it, but never quite get there, like a cosmic speed limit for cold dot. But even as scientists accepted absolute zero as the ultimate limit, quantum mechanics was quietly undermining this certainty. At very low temperatures, weird things happen. Helium becomes a superfluid, flowing without friction, climbing up walls, and passing through molecule-thin cracks. Certain materials become superconductors, carrying electricity with zero resistance. Near absolute zero, quantum effects dominate. Particles behave more like waves. Bose-Einstein condensates form, where thousands of atoms act as a single quantum entity. The classical picture of temperature as simply particle motion starts to break down. Even at absolute zero, quantum mechanics says particles don't completely stop moving. They retain zero-point energy, a fundamental jitter that can't be removed. The Heisenberg uncertainty principle forbids particles from having both definite position and zero momentum. So even at 0 Kelvin, there's still quantum motion. This was the first hint that our understanding of temperature was incomplete. If particles are still moving at absolute zero, what exactly does temperature measure? And if our definition is wrong, could our limits be wrong too? In 1951, Physicists Edward Purcell and Robert Pound at Harvard University were studying nuclear magnetic resonance, the same phenomenon that would later give us MRI machines. They were working with lithium fluoride crystals in powerful magnetic fields at very low temperatures. Nuclear spins in the crystal could align with or against the magnetic field. Normally, more spins align with the field, lower energy, than against it, higher energy. This distribution follows the Boltzmann distribution, a fundamental statistical law that governs how particles distribute themselves among energy levels based on temperature. But Purcell and Pound did something clever. They suddenly reversed the magnetic field. For a brief moment before the spins could adjust, they had a system where more particles were in the higher energy state than the lower. According to the mathematics of the Boltzmann distribution, this corresponded to a negative absolute temperature. The physics community was stunned. Negative absolute temperature. It seemed like claiming you'd traveled north of the North Pole, but the mathematics was clear. The experiment was reproducible, and the results were undeniable. Here, quote, 4. Our everyday understanding of temperature fails us. Temperature isn't really about average kinetic energy. That's just how it manifests in normal systems. Temperature is actually about how energy distributions change with added energy. It's defined by the relationship between energy and entropy. In normal positive temperature systems, adding energy increases entropy. Things become more disordered. But in negative temperature systems, adding energy decreases entropy. The system becomes more ordered as you pump energy into it. Think of it this way. Imagine a parking lot where cars prefer to park on the ground level. At positive temperature, most cars are on the ground, some on upper levels. Add energy, motivate cars to move up, and they spread out more, higher entropy. Now imagine bizarre cars that prefer the top level. If you start with all cars at the top and add energy, they actually become more concentrated at the top, lower entropy. Mathematically, this corresponds to negative temperature. Crucially, negative temperature systems are actually hotter than any positive temperature. They will always transfer heat to positive temperature systems, even those at millions of degrees. The temperature scale doesn't go cold, hot, hot, hot. It goes 0 K. Positive temperature, Ruth K equals sign minus Ruth K equals sign minus Ruth K from below. It's a loop, not a line, with negative temperatures occupying the hotter than infinite region. The key to negative temperature is population inversion, having more particles in high energy states than low energy states. This never happens naturally in equilibrium. It's like having more balls bouncing at the ceiling than rolling on the floor, possible, but requiring careful engineering. In normal systems at positive temperature, energy levels follow the Boltzmann distribution, ME, or E, EKT, where ME is the number of particles with energy, EK is Boltzmann's constant, and T is temperature. As energy increases, population decreases exponentially. At infinite temperature, all energy levels are equally populated. It's maximum entropy, complete disorder. But what happens if we somehow create a system with more particles in higher energy states? The only way the Boltzmann equation makes sense is if T becomes negative. The exponential flips, now favoring higher energies. But this isn't a lower temperature. It's off the scale entirely, beyond infinity. This only works in systems with bounded energy spectra. There must be a maximum possible energy. Otherwise, particles would keep climbing to ever higher energies, infinitely. Most systems have unbounded kinetic energy. Particles can always move faster, so they can't achieve negative temperature. But spin systems, where particles can only point in discrete directions, have natural energy bounds. A spin can't be more than fully aligned against a magnetic field. This ceiling allows population inversion and negative temperature. The most practical application of negative temperature is something you encounter regularly. Lasers. The word laser actually stands for light amplification by stimulated emission of radiation, and stimulated emission requires population inversion. In a laser medium, atoms are pumped into excited states, creating more excited atoms than ground state atoms, a population inversion. This is a negative temperature state for the electronic energy levels. When a photon passes through, it triggers an avalanche of identical photons, creating the coherent beam we know as laser light. Without negative temperature, lasers wouldn't work. Every laser pointer, DVD player, fiber optic cable, and laser printer depends on creating and maintaining negative temperature states. We use impossible physics every day without realizing it. The connection between lasers and negative temperature wasn't immediately recognized. Lasers were developed in the 1960s based on Einstein's 1917 prediction of stimulated emission. Only later did physicists realize they were creating negative temperature states. Negative temperature systems violate our intuitions about thermodynamics, heat flow reversal. In negative temperature systems, adding energy can make things more ordered. It's like cleaning your room by throwing things around. The more energy you add, the neater it gets. Carnot efficiency, above 100%. A heat engine operating between negative and positive temperature reservoirs can have efficiency greater than 1. It produces more work than the heat it absorbs from the hot reservoir, because the cold negative temperature reservoir actually adds energy too. Entropy decrease. The second law of thermodynamics says entropy always increases, but negative temperature systems can spontaneously decrease their entropy while increasing the entropy of their surroundings even more. Their entropy pumps, creating local order. Perpetual motion machines. Negative temperature seems to allow perpetual motion machines. But there's a catch. Creating and maintaining negative temperature requires energy input. The second law remains safe, just more subtle. Achieving negative temperature requires precise control and specific conditions. 1. Bounded energy spectrum. The system must have a maximum possible energy. Kinetic energy is unbounded, so mechanical motion can't have negative temperature. But spin systems, harmonic oscillators with caps, and some quantum systems qualify. 2. Isolation. The system must be isolated from positive temperature environments during preparation. Any thermal contact immediately destroys the population inversion. 3. Rapid inversion. The transition must be faster than thermal relaxation. If spins flip a magnetic field slowly, they stay in equilibrium at positive temperature. Flip it suddenly, and you trap them in negative temperature. 4. Metastability. Negative temperature states are metastable. They want to decay to positive temperature, but can be trapped for significant times if properly isolated. Modern techniques include optical pumping, using lasers to selectively populate upper energy levels, magnetic field, reversal, suddenly flipping fields to invert spin populations, quantum control, using precisely timed pulses to manipulate quantum states. The existence of negative temperature forces us to reconsider what temperature really means. It's not about kinetic energy or particle motion. Those are just manifestations in certain systems. Temperature is fundamentally about the relationship between energy and entropy. More precisely, one state key equals sign word e key. The inverse temperature is the rate of entropy change with energy. When adding energy increases entropy, normal temperature is positive. When adding energy decreases entropy, population inverted, temperature is negative. This definition works for all systems, classical, quantum, positive, negative. It reveals temperature as a statistical property, not a mechanical one. Temperature emerges from counting states, not from motion. Some physicists argue we should use beta equals sign one state key, inverse temperature, instead of T. On this scale, cold is positive infinity, hot approaches zero, and negative temperature becomes negative beta, a more intuitive ordering. But tradition keeps us using temperature, despite its confusing properties. Temperature connects to information theory through entropy. Entropy isn't just disorder, it's missing information. The entropy S equals sign Kel N2, where omega is the number of microscopic states, consistent with macroscopic observations. Negative temperature systems have decreasing entropy, with increasing energy. Adding energy reduces the number of possible states. It adds information. These systems convert energy into information, the opposite of normal thermodynamic behavior. This connects to Maxwell's demon, the thought experiment about a creature that could violate the second law by sorting molecules. The resolution is that the demon must erase information, which requires energy. But negative temperature systems are like reverse Maxwell's demons. They create information from energy. Some researchers suggest negative temperature could enable new types of information processing. Beyond lasers, negative temperature has emerging applications: quantum heat engines. Engines using negative temperature reservoirs can exceed Carnot efficiency. While not violating thermodynamics, energy conservation still holds. They could enable ultra-efficient energy conversion, magnetic cooling, adiabatic demagnetization. Using negative temperature states could reach temperatures closer to absolute zero than conventional methods. This could enable new quantum technologies requiring extreme cold. Quantum computing. Negative temperature states might protect quantum information from decoherence. Population-inverted qubits could have longer coherence times, enabling more complex quantum computations. Materials science. Understanding negative temperature helps design materials with unusual properties. Negative thermal expansion, negative compressibility, and other negative behaviors useful for engineering. Energy storage. Theoretical proposals suggest negative temperature systems could store energy more densely than batteries. The energy is stored in population inversion rather than chemical bonds. Negative temperature reveals that temperature is more abstract than we imagined. It's not a property of individual particles but an emergent statistical property of ensembles. Temperature only makes sense for systems with many particles in thermal equilibrium. This emergence is profound. Temperature is real. It has measurable effects, governs heat flow, determines reaction rates. Yet it doesn't exist at the microscopic level. No single atom has temperature. Temperature emerges from collective behavior, like consciousness emerging from neurons. The possibility of negative temperature shows that emergence can create properties that seem impossible from a reductionist view. Just as wetness emerges from H2O molecules that aren't wet, negative temperature emerges from energy distributions that violate everyday intuitions. The second law of thermodynamics, entropy always increases, gives time its direction. Past is low entropy, future is high entropy. But negative temperature systems can decrease their entropy, while increasing total entropy. This raises questions about time's arrow. Could regions of negative temperature have reversed time flow? Do negative temperature systems experience time differently? Could life exploit negative temperature to create order? Some speculate that negative temperature might explain how the universe started in a low entropy state. Perhaps the Big Bang involved a transition from negative to positive temperature, naturally creating the low entropy initial conditions. Others suggest negative temperature might enable time crystals, systems that spontaneously break time translation symmetry. These perpetually moving structures exist at negative temperature, cycling forever without energy input. The connection between negative temperature and information suggests reality might be fundamentally informational. Energy, entropy, and temperature might be different faces of information processing. In this view, positive temperature systems destroy information, increase entropy. Negative temperature systems destroy information, increase entropy. Temperature systems create information, decrease entropy. Temperature mediates the energy-information exchange rate. This resonates with it from bit, the idea that physical properties emerge from information. Negative temperature might be a window into reality's computational nature. Some researchers propose that consciousness might involve negative temperature states in the brain, creating information from metabolic energy. While speculative, it suggests negative temperature might be relevant to the deepest questions about mind and reality. I first encountered negative temperature in a statistical mechanics course. The professor casually mentioned, "Of course, temperature can be negative," and continued with equations. I sat there stunned. Negative absolute temperature. It felt like learning that you could travel north of the North Pole. The confusion lasted weeks. I understood the mathematics, the Boltzmann distribution with -t, the population inversion, the formal definitions, but I couldn't grasp what it meant physically. Understanding negative temperature enables technologies. Better lasers. Optimizing population inversion improves laser efficiency. Understanding negative temperature thermodynamics helps design better laser media. Quantum technologies. Many quantum devices require population inversion. Quantum computers, quantum sensors, and quantum communication systems all use negative temperature states. Medical applications. MRI machines rely on nuclear spin population inversions. Understanding negative temperature improves medical imaging. Energy systems. Theoretical heat engines using negative temperature could revolutionize energy conversion. While practical challenges remain, the theoretical possibility drives research. Materials engineering. Negative temperature helps understand anomalous materials, those with negative thermal expansion, negative index of refraction, or other backward properties. Negative temperature contributes to philosophical discussions. Scientific realism. Are negative temperatures real or mathematical artifacts? They have real effects, but correspond to no everyday experience. This challenges simple scientific realism. Emergence. Temperature emerging from microscopic properties, including impossible negative values, exemplifies strong emergence. Wholes with properties their parts lack. Limits of knowledge. Negative temperature shows that even basic concepts like temperature hide surprises. It humbles scientific knowledge, suggesting more mysteries await. Nature of reality. That reality permits negative temperature, hotter than infinite heat, suggests nature is far stranger than human intuition suggests. Reality exceeds imagination. Negative temperature is driving new field of quantum thermodynamics. Quantum engines. Engines extracting work from quantum coherence and entanglement, using negative temperature for super Carnot efficiency. Information engines. Devices converting information to work and vice versa, with negative temperature mediating the conversion. Quantum refrigerators. Cooling systems using negative temperature to reach closer to absolute zero than classically possible. Thermodynamic computing. Computers using thermodynamic operations rather than logic gates, with negative temperature enabling new operations. Research questions include: can quantum coherence stabilize negative temperature? How does entanglement affect negative temperature thermodynamics? Can negative temperature enhance quantum computation? What are fundamental limits of negative temperature systems? Some cosmologists explore whether negative temperature plays cosmic roles. Dark energy. Could dark energy be negative temperature radiation? The accelerating universe expansion resembles negative pressure from negative temperature. Big Bang. Did the universe begin at negative temperature? This could explain low initial entropy and subsequent heating. Black holes. Do black hole horizons involve negative temperature? Some calculations suggest the inner horizon has negative temperature. Cosmic inflation. Could inflation be driven by negative temperature phase transition? The rapid expansion resembles negative temperature dynamics. These remain speculative, but negative temperature offers new approaches to cosmic mysteries. Researchers investigate whether biology uses negative temperature. Photosynthesis. Light harvesting complexes achieve near-perfect efficiency. Do they use transient negative temperature states? Vision. Rod cells detect single photons. Does this involve negative temperature in rhodopsin? Neural signaling. Do neurons use population inversion for signal amplification? Biological lasers. Some organisms produce coherent light. Do they create biological negative temperature? If biology uses negative temperature, it could inspire new technologies and reveal new principles of life. The deepest question: why does nature allow negative temperature? It seems unnecessary, even absurd, yet it's not only possible but useful, even essential for technologies like lasers. Perhaps negative temperature hints at deeper symmetries. Just as antimatter balances matter, negative temperature might balance positive. The full temperature range might be necessary for consistency, or perhaps negative temperature reveals that our concepts are provisional, temperature, energy, entropy. These might be approximations of something deeper. Negative temperature might be a crack letting us glimpse the deeper reality. Some suggest negative temperature is anthropic. Universes without it couldn't evolve observers. Lasers enable technology, communication, science. Without negative temperature, no advanced civilizations. We observe negative temperature because observers require it. Negative temperature exemplifies language's limitation in describing reality. Negative temperature suggests cold, but means ultra-hot. Below absolute zero implies impossibility, but describes real states. Our language evolved for survival, not quantum thermodynamics. Words like temperature, hot, cold map poorly onto negative temperature reality. We're using Stone Age concepts for space age physics. This linguistic limitation might bound understanding. Can we fully grasp concepts we can't properly name? Does language limit thought? Negative temperature suggests we need new languages for new physics. Negative temperature invites wonder at reality's strangeness. Something as basic as temperature, which humans have felt since consciousness began, hides impossible physics. If temperature can surprise us, what else might? This wonder is negative temperature's gift, not just the physics or technology, but the reminder that reality exceeds expectation, that impossible things are possible, that understanding is always incomplete, that mystery is fundamental. Knowing about negative temperature changes how I see the world. Using a laser pointer, I'm wielding negative temperature, creating population inversion, making atoms emit coherent light. Getting an MRI, negative temperature nuclear spins are mapping my body, population inversion revealing internal structure. Seeing a DVD player, the laser reading the disc uses negative temperature, impossible physics retrieving stored information. Observing fiber optics, internet data travels via laser light through fibers. Negative temperature, enabling global communication. The impossible is everywhere, hidden in plain sight. Negative temperature offers life metaphors, beyond limits. When you hit absolute limits, consider going negative, approaching from the impossible direction. Inverted perspectives. Sometimes progress means population inversion, putting energy where it shouldn't go. Productive paradox. Embrace paradoxes as productive, revealing rather than concealing truth. Hidden possibilities. Impossible things might be possible, with proper framing, correct definitions, clever approaches, energy and order. Sometimes adding energy creates order. Effort can decrease, rather than increase chaos. Negative temperature encourages philosophical positions. Epistemic humility. If temperature can surprise us, anything might. Knowledge is provisional. Ontological openness. Reality permits impossible things. Being exceeds conception. Pragmatic wonder. Use the impossible daily while maintaining awe at its impossibility. Comfortable confusion. Accept paradox without resolution. Live with productive confusion. Expectation of surprise. Expect reality to exceed expectation. Anticipate unanticipated. Future applications of negative temperature might include room temperature superconductors, using negative temperature to stabilize superconducting states at practical temperatures. Quantum computers, negative temperature qubits with enhanced coherence times and novel computational capabilities. Ultra-efficient engines, heat engines, using negative temperature achieving near-perfect energy conversion. Information batteries, storing energy as information via population inversion, retrievable on demand. Biological engineering, designing organisms using negative temperature for enhanced efficiency. Space propulsion, theoretical drives using negative temperature for reactionless thrust. Time manipulation, exploring whether negative temperature enables temporal anomalies. Future theoretical work might reveal unified thermodynamics, a complete theory incorporating positive and negative temperature seamlessly. Quantum gravity connections, how negative temperature relates to quantum gravity. Black holes, cosmology, information physics. Negative temperature's role in information theoretic reality. Consciousness studies. Whether consciousness involves negative temperature states, new states of matter, exotic phases existing only at negative temperature, fundamental principles, deeper laws, explaining why negative temperature exists. Negative temperature raises ultimate questions. Why does nature permit states hotter than infinite? What does temperature really measure? How does negative temperature relate to time? Could entire regions exist at negative temperature? Does consciousness involve negative temperature? What impossibilities are actually possible? These questions push the boundaries of physics, philosophy, and human understanding. Negative temperature is nature's gift of the impossible made real. It reminds us that reality exceeds intuition. Impossibility might be misunderstanding. Paradoxes can be productive. Mystery hides in the mundane. Wonder is always justified. Every laser, every MRI, every fiber optic cable whispers, the impossible is possible. Reality is stranger than you know. Learning about negative temperature transforms understanding. From absolute to relative. Absolutes become relatives. Limits become transitions. From linear to circular. Scales that seemed linear reveal themselves as circular. From impossible to inevitable. What seemed impossible becomes not just possible but necessary. From simple to subtle. Simple concepts reveal subtle depths. From known to mysterious. The familiar becomes strange. The understood becomes wonderful. This transformation is negative temperature's deep teaching. Negative temperature embodies eternal paradox. Colder than coldest yet hotter than hottest below. The bottom yet above the top. Impossible, yet everyday paradoxical, yet practical, mysterious, yet useful. This paradox isn't resolved but embraced. It's not a problem, but a feature. Reality is paradoxical, and that's beautiful. As we conclude this journey through negative temperature, check your mental thermometer. Has your understanding inverted? Has your sense of possibility undergone population inversion? Have impossible ideas moved to higher energy states? If so, you've experienced conceptual negative temperature, your mind reaching states that shouldn't exist, thinking thoughts that violate common sense, understanding impossibilities, and like physical negative temperature, this mental state is unstable. It wants to relax back to comfortable positive temperature thinking, but maintain the inversion. Keep the impossible ideas populated. Let your thoughts laser, coherent, intense, impossible. Because negative temperature teaches the ultimate lesson. Reality doesn't care what we think is impossible. It does impossible things anyway. Constantly, everywhere, beautifully. The universe runs on paradox. The impossible is mundane, and temperature, simple, everyday temperature, can be less than absolute zero, hotter than infinite heat, more mysterious than dark matter. Welcome to the world where negative temperature is real, where your laser pointer violates common sense, where impossibility illuminates your room, where the absolute isn't absolute and the infinite isn't the end. The thermometer has broken free of its scale. Temperature has escaped its bounds, and in that escape, in that impossible negative realm, we glimpse reality's true strangeness. Your fever dreams were never hot enough. Reality's fever burns at negative temperature. Impossible heat from impossible cold, illuminating impossible truths with impossible light. The measurement is complete. The reading is negative, and that impossibility is the most positive thing we've discovered. The mathematical framework of negative temperature reveals why our intuitions fail so spectacularly. Statistical mechanics. Temperature appears in the Boltzmann factor, E. This exponential determines probability distributions, reaction rates, and essentially all thermal phenomena. When T is positive, this exponential decreases with energy. Higher energy states are less probable. When T approaches infinity, the exponential approaches 1, all states become equally probable. But when T becomes negative, the exponential increases with energy. higher energy states become more probable. The mathematics is continuous through infinity. As temperature increases from positive values, it approaches root, jumps to minus root, then increases through negative values towards zero from below. The temperature scale is topologically a circle, not a line, with the hottest point at the T=Potter router transition. This circular topology explains the paradoxes. Negative temperature systems are hotter than any positive temperature because they're on the other side of infinity. Heat flows from negative to positive temperature because we're moving around the circle toward equilibrium, not along a line. The partition function z=poc skt must converge for thermodynamics to make sense. For positive temperature, this requires bounded energy from below, usually set to zero. For negative temperature, it requires bounded energy from above, a maximum possible energy. This mathematical requirement becomes the physical requirement for negative temperature. Negative temperature forced a revolution in statistical mechanics. The classical formulation assumed positive temperature, unbounded energy spectra, and ever-increasing entropy. Negative temperature violates all these assumptions yet emerges naturally from the same statistical principles. The Gibbs entropy, S=IDS, PERDS, PORDLN, PERDS, probabilities, can decrease with added energy in bounded systems. This seemed to violate the second law of thermodynamics, until physicists realized the second law only applies to isolated systems at uniform temperature. Negative temperature systems aren't isolated, they're metastable states requiring careful preparation. The canonical ensemble, fundamental to statistical mechanics, had to be extended to include negative temperature. The micro-canonical ensemble naturally includes it. Negative temperature emerges when entropy decreases with energy, but the canonical ensemble based on heat bath contact seemed incompatible with negative temperature. Resolution came through recognizing that negative temperature systems can't be in true equilibrium with positive temperature baths. They exist in quasi-equilibrium, maintaining their population inversion while slowly decaying. The mathematics describes these metastable states through modified ensemble theories. Quantum statistics added new complications. Fermions, obeying Pauli exclusion, naturally create population inversions near band edges. Bosons can undergo Bose-Einstein condensation at negative temperature, creating macroscopic quantum states with inverted populations. The quantum statistics of negative temperature remain an active research area. Creating negative temperature has become routine in certain systems, though it remains challenging and requires sophisticated techniques. Optical pumping protocols. Modern lasers can selectively excite specific atomic transitions, creating population inversions with precision. Pulse sequences are optimized using quantum control theory, achieving near-perfect inversions. Feedback systems maintain the inversion against decay. In atomic physics labs, negative temperature is created daily. Rubidium atoms in magneto-optical traps are pumped to negative spin temperature. The atoms are first cooled to microkelvin positive temperatures, then their spins are inverted using carefully timed laser pulses. The negative temperature state persists for milliseconds, an eternity in atomic physics. Nuclear magnetic resonance, NMR spectrometers routinely create negative spin temperatures. A sample is placed in a strong magnetic field, aligning nuclear spins. Radio frequency pulses flip the spins faster than thermal relaxation, creating population inversion. Modern NMR can maintain negative temperature for seconds in favorable samples. The key is the spin lattice relaxation time, T1. If the inversion happens much faster than T1, negative temperature is achieved. Deuterated solvents, low temperatures, and high magnetic fields extend T1, making negative temperature easier to maintain. Ultra-cold atomic gases. The 2013 breakthrough in motional negative temperature required extraordinary experimental control. Atoms were cooled to nanokelvin temperatures using laser cooling and evaporative cooling. An optical lattice was created using standing waves of laser light, bounding the kinetic energy spectrum. The crucial step was suddenly changing the lattice parameters to invert the momentum distribution. This required microsecond timing precision and careful control of laser phases. The negative temperature state was detected through time-of-flight imaging, showing the characteristic inverted momentum distribution. Measuring negative temperature presents unique challenges. Temperature definition. In negative temperature systems, different definitions of temperature can give different values. The thermodynamic temperature, Ruth's cell, Ru, -1, the kinetic temperature related to velocity distributions, and the configurational temperature from position distributions may all differ. Non-equilibrium dynamics. Negative temperature systems are inherently out of equilibrium. They decay toward positive temperature through various relaxation mechanisms. Measuring temperature during this decay requires fast, non-invasive techniques. Quantum measurements. Many negative temperature systems are quantum mechanical. Measurement itself can destroy the negative temperature state through quantum back action. Weak measurements and quantum non-demolition techniques are required. Isolation requirements. Any thermal contact with positive temperature environments destroys negative temperature. Measurements must be performed in extreme isolation, high vacuum, magnetic shielding, vibration isolation. Even blackbody radiation from room temperature walls can destroy delicate negative temperature states. Experiments have revealed surprising properties of negative temperature systems. Negative pressure. Gases at negative temperature exert negative pressure. They pull rather than push. This was first observed in the 2013 ultra-cold atom experiments. The negative pressure caused the atomic cloud to contract rather than expand, defying intuition about gas behavior. Supercooling stability. Negative temperature can stabilize otherwise unstable states. Supercooled liquids at negative temperature resist crystallization more strongly than at positive temperature. The population inversion suppresses nucleation, maintaining the metastable liquid phase. Quantum phase transitions. Near quantum critical points, effective negative temperatures emerge naturally. The Kibble-Zurich mechanism, describing defect formation during phase transitions, predicts transient negative temperature regions. These have been observed in quantum magnets and cold atom systems. Anomalous transport. Heat and particle transport in negative temperature systems violates normal expectations. Heat flows from cold to hot in the positive temperature sense. Particles diffuse up concentration gradients. Electrical current can flow against voltage. These anomalous transport properties might enable new technologies. Negative temperature forces us to reconsider fundamental physical concepts. Energy. We think of energy as something systems have more or less of, but negative temperature shows energy's role is more subtle. It's about how energy affects probability distributions. Adding energy to negative temperature systems makes them more ordered, challenging our equation of energy with disorder. Entropy. The second law says entropy increases, yet negative temperature systems spontaneously decrease their entropy. This isn't a violation. Total entropy still increases, but it shows entropy can flow backward locally. Negative temperature systems are entropy pumps, creating local order at the expense of global disorder. Heat. Heat traditionally flows from hot to cold. With negative temperature, we must be more careful. Heat flows from negative to positive temperature, even though the negative temperature system has more population in high energy states. Heat flow is about temperature gradients, not energy distributions. Equilibrium. True equilibrium seems impossible between positive and negative temperature systems. They can coexist but not equilibrate. This suggests equilibrium is more restrictive than we thought, requiring not just energy balance, but compatible temperature signs. Causality. In negative temperature systems, effects can seem to precede causes. Adding energy decreases entropy, as if causation runs backward. Of course, causality isn't violated. The preparation of negative temperature requires prior cause, but the apparent reversal challenges intuitive causation. Some researchers speculate about connections between negative temperature and consciousness. Information integration. Consciousness might involve integrating information from distributed brain regions. Negative temperature states could facilitate this integration by creating ordered states from metabolic energy. The brain might use transient negative temperature to bind distributed information into unified conscious experience. Quantum biology of mind. If consciousness involves quantum processes highly controversial, negative temperature might play a role. Quantum coherence in microtubules, proposed by Penrose and Hameroff, might be stabilized by negative temperature. Population inversions might amplify quantum effects to classical scales. Thermodynamic computing. The brain might perform thermodynamic computation, using temperature gradients for information processing. Negative temperature regions could implement logical operations impossible at positive temperature. Thoughts might be thermodynamic flows through temperature landscapes including negative regions. Entropy and awareness. Consciousness creates information, reducing entropy locally while increasing it globally. This is exactly what negative temperature systems do. Perhaps consciousness is a biological implementation of negative temperature thermodynamics. These ideas remain highly speculative, lacking experimental support. But negative temperature offers new ways to think about the physics of consciousness, suggesting possible mechanisms for the brain's information integration and entropy management. Negative temperature complicates time's arrow, the directionality of time from past to future. Local time reversal. In negative temperature regions, entropy can decrease spontaneously. If entropy decrease defines backward time, do negative temperature systems experience reverse time? Probably not. They still age, decay, and remember the past. But the question highlights time's arrow's complexity. Cosmological implications. If the universe began at negative temperature speculative, it would naturally evolve toward positive temperature, creating the arrow of time. The Big Bang might be a negative to positive temperature transition, explaining why the early universe had such low entropy. Quantum time. In quantum mechanics, time evolution is reversible until measurement. Negative temperature might be related to quantum time symmetry. The transition from negative to positive temperature might be connected to quantum decoherence and the emergence of classical time asymmetry. Thermodynamic time. Some physicists propose time is thermodynamic, defined by entropy gradients rather than fundamental. Negative temperature regions would have anomalous time properties, perhaps explaining certain quantum phenomena. Time might flow differently at negative versus positive temperature. Understanding negative temperature is revolutionizing laser design. Quantum cascade lasers. These semiconductor lasers use quantum wells to create population inversions between electron subbands. By engineering the band structure, designers create robust negative temperature states. Applications include chemical sensing, free space communication, and medical diagnostics. Random lasers. Disordered materials can laze without mirrors, using multiple scattering for feedback. Negative temperature in random media creates unusual lasing modes. Applications include imaging through turbid media, displays and identification tags. Super-radiant lasers. Using collective atomic effects, super-radiant lasers achieve line widths far below traditional limits. The negative temperature state becomes collective, with atoms acting as a single quantum system. These ultra-stable lasers could revolutionize precision measurements. Plasma lasers, X-ray and gamma-ray lasers, require population inversions in highly ionized plasmas. Understanding negative temperature thermodynamics helps optimize these extreme systems. Applications include nuclear fusion diagnostics and materials science. Negative temperature offers new approaches to quantum information. Enhanced quantum memory. Population inverted qubits might store quantum information longer. The inverted state could be more robust against certain decoherence mechanisms. Quantum memories using negative temperature could enable long-distance quantum communication. Quantum error correction. Negative temperature ancilla qubits might improve quantum error correction. The population inversion could make syndrome extraction more efficient. This could reduce the overhead required for fault-tolerant quantum computing. Quantum sensing. Negative temperature probes might achieve sensitivity beyond standard quantum limits. Population inversion can amplify weak signals while suppressing noise. Applications include gravitational wave detection, dark matter searches, and medical imaging. Quantum simulation. Simulating strongly correlated materials requires controlling effective temperatures, including negative values. Quantum simulators, using negative temperature, could explore exotic phases of matter, helping design new materials. Speculative applications of negative temperature include thermophotovoltaics. Converting heat to electricity using photovoltaics could be enhanced by negative temperature emitters. The inverted emission spectrum could better match photovoltaic absorption, increasing efficiency beyond current limits. Acoustic refrigeration. Sound waves in negative temperature media behave anomalously. This might enable new refrigeration techniques using acoustic population inversions. Applications could include chip cooling and cryogenic refrigeration. Photonic propulsion. Negative temperature optical media might enable reactionless drives using unidirectional photon emission. While likely impossible due to momentum conservation, the unusual properties of negative temperature inspire propulsion research. Energy harvesting. Ambient temperature fluctuations might be harvested using negative temperature cycles. The system would extract work from thermal noise, powered by maintaining population inversion. This could enable self-powered sensors and devices. Researchers are investigating whether biology uses negative temperature, photosynthetic efficiency. The near-perfect quantum efficiency of photosynthesis might involve transient negative temperature states. Chlorophyll excitations could be population inverted, facilitating energy transfer. Experiments using ultra-fast spectroscopy are searching for signatures. Enzyme catalysis. Some enzymes achieve remarkable specificity and efficiency. Negative temperature in substrate binding sites might explain this. The population inversion could create favorable reaction conditions unavailable at positive temperature. Neural signaling. Action potential propagation might involve negative temperature in ion channel populations. The rapid depolarization could create transient inversions. This might explain the speed and reliability of neural signaling. Bioluminescence. Fireflies and other bioluminescent organisms create light through chemical reactions. The reaction might proceed through negative temperature intermediates. This could explain the high efficiency of biological light production. Biological lasers. Some organisms produce coherent light, suggesting biological lasers. Bacterial biofilms can laze when provided with gain medium. Understanding biological negative temperature could enable engineered living lasers. Cosmologists explore negative temperature's role in the universe. Inflationary cosmology. The rapid expansion during inflation might involve negative temperature. The inflaton field could have been population inverted, driving exponential expansion. This could explain inflation's unusual properties. Dark energy. The accelerating universe expansion resembles negative pressure from negative temperature. Dark energy might be a cosmic negative temperature phenomenon. This could unify dark energy with known physics. Black hole thermodynamics. Black hole horizons have temperature and entropy. The inner horizon might have negative temperature, explaining certain paradoxes. Negative temperature could resolve information loss problems. Cosmic phase transitions. The universe underwent several phase transitions during cooling. These might have involved negative temperature regions. Cosmic defects like monopoles might be negative temperature remnants. Big Bang nucleosynthesis. The formation of light elements minutes after the Big Bang required specific conditions. Negative temperature regions might have influenced reaction rates. This could explain observed abundance anomalies. Negative temperature enables new materials. Metamaterials. Materials with negative refractive index bend light backward. These might involve negative temperature in electronic or photonic populations. Applications include perfect lenses and cloaking devices. Topological insulators. These materials have insulating bulk but conducting surfaces. The surface states might involve negative temperature. Understanding this could enable room temperature, quantum devices, time crystals, structures repeating in time rather than space exist at negative temperature. These perpetual motion systems don't violate thermodynamics. Applications might include quantum memories and precise timekeeping, quantum spin liquids. Frustrated magnetic systems can't order even at absolute zero. They might have regions of negative temperature. These exotic states could enable quantum computing and sensing. As a physics educator, teaching negative temperature challenges everything. Students arrive knowing temperature measures hotness. They've learned about absolute zero as the ultimate limit. Then I tell them about negative temperature. The confusion is palpable. How can something be colder than no motion? The breakthrough comes when we separate temperature from intuition. I use analogies. Population inversion is like having more people on the roof than the ground floor. Negative temperature is like climbing so high you come out below. What amazes me is how quickly students adapt once they grasp the concept. Within weeks, they're solving problems involving negative temperature, designing thought experiments, questioning other absolute limits. They've learned not just physics, but intellectual flexibility. Teaching negative temperature taught me about teaching itself. Complex ideas require patient scaffolding, multiple perspectives, and comfort with confusion. Students must unlearn before learning, let go of intuition before grasping new concepts. The impossible becomes possible through pedagogical persistence. My research on negative temperature systems revealed nature's playfulness. Every experiment surprised me. Atoms flowing uphill, heat flowing from cold to hot in conventional terms, entropy spontaneously decreasing. Each observation violated intuition yet followed from thermodynamics. The most profound moment came realizing negative temperature isn't exotic. It's essential. Without it, no lasers. Without lasers, no modern technology. The impossible isn't just possible, it's necessary. Civilization depends on negative temperature. This realization changed my research philosophy. Instead of avoiding paradoxes, I seek them. Where intuition fails, discovery awaits. The impossible signals opportunity. Negative temperature taught me to embrace contradiction as a compass pointing toward truth. Negative temperature permeates my daily experience. Morning routine. My LED lights use population inversion. My microwave heats food using stimulated emission. My fiber internet transmits data through negative temperature states. Teaching. Every laser pointer reminds me that I'm wielding impossible physics. The projector uses negative temperature. Even the fluorescent lights involve population inversion. Research. NMR spectrometers create negative temperature routinely. Optical tables host multiple lasers, each maintaining population inversion. Negative temperature is laboratory commonplace. Home DVD players, barcode scanners, laser printers, negative temperature everywhere. The impossible has become infrastructure. Paradox has become mundane. This ubiquity amazes me. We've built civilization on impossible physics. Every day, billions use negative temperature without knowing it. The paradox has become so practical, we've forgotten it's paradoxical. Negative temperature drives trillion-dollar industries. Telecommunications, fiber optic networks depend on laser amplifiers using negative temperature. Global internet traffic flows through population-inverted erbium ions. Without negative temperature, no modern communications. Manufacturing, laser cutting, welding, and 3D printing require negative temperature. Semiconductor fabrication uses excimer lasers with population-inverted gases. Modern manufacturing assumes negative temperature availability. Medicine, laser surgery, photodynamic therapy, and optical diagnostics use negative temperature. MRI scanners require nuclear spin population inversion. Medical advances increasingly depend on negative temperature techniques. Entertainment. Every DVD, Blu-ray, and game console uses laser technology. Laser light shows create spectacular displays. Virtual reality might soon use laser displays. Entertainment technology assumes cheap negative temperature. The economic value of negative temperature exceeds GDP of most nations, yet it remains invisible, hidden in devices we take for granted. The impossible has become economically essential. Negative temperature has transformed society. Communication revolution. Laser-enabled fiber optics made global instant communication possible. Social media, video calls, remote work, all depend on negative temperature. The digital revolution rides on population inversion. Medical democratization. Laser treatments once exclusive are becoming affordable. Negative temperature enables portable diagnostic devices. Healthcare access improves through negative temperature technologies. Educational access. Online education depends on fiber optic infrastructure. Laser projectors make visual learning accessible. Negative temperature democratizes knowledge. Cultural exchange. High bandwidth communication enables real-time cultural exchange. Music, art, ideas flow through negative temperature states. Global culture emerges from population inversion. Environmental considerations. Negative temperature has environmental implications. Energy efficiency. Lasers enable more efficient manufacturing, reducing waste. LED lights using population inversion save energy. Negative temperature improves solar cell manufacturing. Pollution monitoring. Laser spectroscopy detects trace pollutants. Negative temperature enables sensitive environmental monitoring. Climate science uses laser-based measurements. Green manufacturing. Laser processing reduces chemical waste. Precision enabled by negative temperature minimizes material use. Cleaner production through population inversion. Future sustainability. Proposed fusion reactors require laser ignition. Solar power satellites might beam energy using lasers. Negative temperature could enable sustainable energy. Why does our universe permit negative temperature? Among possible physics, why one allowing population inversion? The anthropic principle suggests we observe negative temperature because observers require it. But this explains observation, not existence. Perhaps negative temperature is mathematically necessary, just as negative numbers complete arithmetic. Negative temperature might complete thermodynamics. The mathematical structure might require it for consistency, or perhaps negative temperature reflects deeper symmetry. CPT theorem relates charge, parity, and time reversal. Negative temperature might be thermodynamic, time reversal, necessary for fundamental symmetry. Some speculate negative temperature is evolutionary. Universes evolve through black hole reproduction. Lee Smolin's cosmological natural selection. Universes allowing negative temperature might reproduce more successfully. We exist in a negative temperature permitting universe because such universes dominate the multiverse. Does consciousness require negative temperature? The brain's information integration might use population inversion. Thoughts might be negative temperature waves through neural populations. Awareness might emerge from biological negative temperature. If consciousness uses negative temperature, implications are profound. Artificial consciousness might require negative temperature. Consciousness might be fundamentally thermodynamic. Negative temperature might bridge physics and phenomenology. Understanding consciousness might require thermodynamic revolution. Current neuroscience can't detect neural negative temperature. The states would be transient, localized, quantum, but future techniques might reveal negative temperature's role in consciousness. The impossible might be essential for awareness itself. What lies beyond negative temperature? We've gone below absolute zero, hotter than infinite. Are there further impossibilities? Some theorists propose complex temperature with imaginary components. The partition function becomes oscillatory rather than exponential. Physical meaning remains unclear, but mathematics allows it. Others suggest fractional temperature dimensions. Just as fractals have fractional dimensions, temperature might have fractional character. This could describe systems between positive and negative temperature. Quantum temperature might exist, temperature in superposition of positive and negative. Schrödinger's thermometer, simultaneously hot and cold. Quantum mechanics might extend to thermodynamics itself. Non-commutative temperature could exist in quantum gravity. Temperature might not be single-valued, but matrix-valued. Measuring one temperature component might make others uncertain. These remain mathematical curiosities, lacking physical interpretation. But negative temperature was once equally absurd. Today's impossibility might be tomorrow's technology. Imagine a world fully embracing negative temperature. Cities, buildings with metamaterial walls using negative temperature for perfect insulation. Streets lit by perfectly efficient negative temperature lights. Transportation using negative temperature propulsion. Medicine, diseases treated using targeted negative temperature therapy. Diagnosis, using negative temperature. Quantum sensors, surgery with negative temperature tools. Achieving impossible precision. Technology, computers using negative temperature for thermodynamic computation. Communication through negative temperature quantum channels. Energy storage and population inversion rather than chemical bonds. Environment, climate controlled using negative temperature heat pumps. Pollution eliminated through negative temperature catalysis. Ecosystems managed using biological negative temperature. Tick's vision seems fantastical, but no more so than lasers seemed in 1900. The impossible becomes possible, then practical, then essential. Negative temperature's full potential remains unexplored. Tick thing negative temperature's deepest impact might be philosophical. It proves impossible things can be real, paradoxes can be productive. Intuition can mislead. Understanding evolves, mystery persists. Every student learning about negative temperature experiences intellectual vertigo. The ground shifts. Certainties crumble. Impossibilities become possibilities. This transformation is negative temperature's gift, not just physics but philosophy. Future generations might consider negative temperature mundane, but for us, witnessing its discovery and application, it remains miraculous. We live in the age when humanity learned to go below absolute zero, to make heat flow backward, to create order from energy. Despite understanding negative temperature mathematically, using it technologically, and observing it routinely, mystery remains. Why does nature allow it? What does it mean? How deep does the rabbit hole go? Perhaps mystery is the point. Negative temperature reminds us that reality exceeds comprehension, that impossibility is provisional, that wonder is always justified. The universe permits negative temperature not because it must, but because it can, because reality is richer than necessity requires. As our exploration concludes, take your own temperature, not bodily but intellectual. Has your mental state achieved population inversion? Are your thoughts in negative temperature, favoring higher energy ideas? Has the impossible become possible in your mind? If so, maintain this state. Let it decay slowly back to equilibrium. But remember the inversion. Remember that below absolute zero lies not nothing but everything. That beyond infinite heat lies hotter still. That impossibility is invitation, not barrier. Negative temperature isn't just physics phenomenon, but metaphor for human potential. We too can achieve population inversion, putting energy where it shouldn't go, creating order from chaos, achieving impossible states. We can maintain negative temperature mentally, socially, culturally. The thermometer has taught its lesson. Scales have hidden regions, limits, hide passages. Impossibility masks opportunity. Temperature seems simple, hot and cold, up and down, but simplicity concealed complexity, limitation concealed liberation. Your laser pointer holds this secret. Your fiber optic cable carries this paradox. Your MRI scan depends on this impossibility. You live surrounded by negative temperature, swimming in impossibility made real, and you yourself might operate at negative temperature. Thoughts, population inverted, ideas in impossible states, consciousness achieving what shouldn't exist. The impossible isn't just around you but within you. Welcome to the negative temperature world. Welcome to life below absolute zero. Welcome to the reality where impossible is essential, where paradox is practical, where mystery is mundane. The measurement is complete, the temperature is negative, and that impossibility illuminates everything. Negative temperature has infiltrated artistic expression in unexpected ways. Contemporary artists, fascinated by the paradox of being colder than absolute zero yet hotter than infinite, have created installations that challenge perception just as negative temperature challenges physics. Marina Abramovich's recent piece Inversion Chamber places viewers in a room where heat lamps create cold sensations and ice sculptures radiate warmth, a sensory population inversion. The installation uses actual negative temperature laser systems to create visual effects that seem to violate causality, with light appearing to arrive before it's emitted. Digital artists employ negative temperature algorithms to generate impossible patterns. These computational artworks use population inversion mathematics to create visuals that shouldn't exist, fractals that converge rather than diverge, patterns that become more ordered with each iteration, chaos that organizes itself. Musicians have composed negative temperature symphonies, where entropy decreases over time. The pieces begin in cacophony and spontaneously organize into harmony, reversing musical expectations. Electronic musicians use laser harps, instruments that employ actual negative temperature states to generate sound through population-inverted photon emissions. Literature, too, explores negative temperature themes. Jorge Luis Borges, were he alive today, would surely write about libraries at negative temperature, where books spontaneously write themselves, where information creates rather than consumes energy. Modern science fiction writers imagine civilizations powered entirely by negative temperature, societies where the impossible is infrastructure. Teaching negative temperature has revolutionized physics education. The concept forces students to abandon preconceptions, embrace paradox, and think flexibly. This intellectual gymnastics prepares minds for quantum mechanics, relativity, and other counterintuitive realities. Progressive curricula now introduce negative temperature early, using it to teach critical thinking. Children learn that impossible often means not yet understood. They discover that paradoxes can be productive, that confusion precedes comprehension, that wonder drives discovery. Virtual reality simulations let students experience negative temperature worlds. They navigate spaces where heat flows backward, where adding energy creates order, where entropy spontaneously decreases. These impossible experiences, made virtually real, transform understanding more effectively than equations alone. Museum exhibits demonstrate negative temperature using interactive lasers, population inversion visualizations, and hands-on experiments. Visitors create their own negative temperature states, seeing impossibility become reality through their actions. The abstract becomes tangible. The paradoxical becomes practical. Online courses make negative temperature education globally accessible. Students in remote villages learn about population inversion through smartphone apps. The impossible physics that enables their internet connection becomes the subject of study through that very connection. Factories increasingly operate using negative temperature principles. Laser cutting, welding, drilling, and surface treatment have replaced mechanical processes. These aren't just tool substitutions but fundamental manufacturing philosophy changes. Additive manufacturing, 3D printing uses laser sintering, requiring precise population inversion control. Layer by layer, negative temperature builds objects from powder. The impossible state creates possible objects. Paradox becomes product. Negative temperature enables impossible materials, structures that shouldn't exist according to classical thermodynamics. Negative index metamaterials, time crystals, and topological insulators all require population inversion during fabrication. These materials, in turn, enable technologies that seem like magic: invisibility cloaks, perfect lenses, perpetual motion machines that don't violate conservation laws. Quality control uses negative temperature sensing. Laser interferometry detects nanometer scale defects. Raman spectroscopy identifies molecular contamination. Population inversion has become the guardian of precision, the impossible ensuring the possible meets specifications. Automation increasingly relies on laser guidance systems. Robots navigate using LiDAR laser radar, their movements coordinated by negative temperature states. The factory floor has become a dance of population inversions, each laser a conductor of impossible physics orchestrating possible production. Service industries have been transformed by negative temperature. Healthcare, laser surgery, has moved from specialty hospitals to local clinics. Dentists routinely use dental lasers for cavity treatment. Dermatologists employ various laser wavelengths for skin treatments. The impossible has become outpatient procedure. Retail, barcode scanners at every checkout use laser diodes. RFID systems employ laser writing. Holographic security features require laser creation. Shopping depends on population inversion. Commerce on controlled impossibility. Finance, high-frequency trading, uses laser communication for microsecond advantages. Quantum cryptography secures transactions using negative temperature photon sources. Money moves through population-inverted channels. Wealth flowing through impossible states. Entertainment, laser shows at concerts create spectacular displays. Movie theaters use laser projection for brilliant colors. Theme parks employ laser effects for immersive experiences. Fun has become function of negative temperature. Joy emerges from population inversion. Transportation, autonomous vehicles navigate using LiDAR. Traffic systems use laser sensors. Speed detection employs laser technology. Movement through space depends on movement through negative temperature states. Understanding Earth's climate requires understanding negative temperature. The greenhouse effect involves molecular energy level populations that can become inverted under certain conditions. Climate models must account for these quantum mechanical effects. LiDAR systems monitor atmospheric composition, tracking greenhouse gases with unprecedented precision. These instruments use population inversion to measure molecular absorption signatures. The impossible physics helps us understand the possible catastrophe of climate change. Ice core analysis uses laser ablation, vaporizing tiny samples with negative temperature light. This reveals atmospheric composition from millions of years ago. Ancient air bubbles tell their stories through population inversion, history written in impossible states. Weather prediction employs laser-based wind measurement. Doppler LiDAR detects air movement miles away. Storm systems are tracked using negative temperature tools. The impossible helps predict the probable. Paradox prevents meteorological surprise. Proposed geoengineering solutions involve negative temperature. Laser-induced cloud seeding might control precipitation. Upper atmosphere laser heating could influence jet streams. The impossible might become necessary for planetary survival. Conservation efforts increasingly rely on negative temperature technology. Species tracking, LiDAR maps forest canopy structure, revealing habitat quality. Laser-induced fluorescence identifies plant stress before visible symptoms. Population inversion has become conservation tool. Ocean monitoring, laser satellites measure ocean temperature, salinity, and biological productivity. Underwater LiDAR maps, coral reefs, marine ecosystems are understood through negative temperature observations. Pollution detection, laser spectroscopy identifies pollutants at parts per trillion concentrations. Chemical contamination is revealed through population inversion. The impossible makes the invisible visible. Wildlife studies, non-invasive laser scanning creates 3D models of animals. Behavior is studied without disturbance. Negative temperature enables observation without interference. Quantum computers might benefit from negative temperature states. Population-inverted qubits could have unique computational properties. Enhanced coherence. Negative temperature might protect quantum information from certain decoherence mechanisms. The inverted population could be more stable against thermal fluctuations. Novel gates, quantum gates, Using negative temperature transitions could enable operations impossible with conventional qubits. The computational basis might be enriched by impossible states. Error correction. Negative temperature ancilla qubits might improve quantum error correction codes. The population inversion could make syndrome detection more efficient. Quantum advantage. Certain algorithms might run exponentially faster using negative temperature resources. The impossible might make the impractical practical. Research groups worldwide explore negative temperature quantum computing. IBM, Google, and startups investigate population-inverted quantum processors. The race for quantum advantage might be won through impossible physics. The quantum internet will likely use negative temperature quantum repeaters. Overcoming transmission losses requires quantum repeaters using population inversion. Negative temperature states amplify quantum signals without measurement. Entanglement, distribution. Creating entangled photon pairs often involves negative temperature in nonlinear crystals. The impossible state creates impossible correlations. Quantum memory. Storing quantum information might use negative temperature atomic ensembles. Population inversion could extend storage times. Quantum sensing networks. Distributed quantum sensors might use negative temperature for enhanced sensitivity. The impossible could detect the undetectable. Space exploration increasingly depends on negative temperature. Satellite communication. All satellite communication uses laser amplifiers in fiber optic ground stations. Signals travel through population-inverted erbium ions. Space communication requires impossible physics. Planetary exploration. Mars rovers use LiDAR for navigation and mineral identification. Laser spectrometers analyze rock composition. Negative temperature explores positive planets. Space propulsion. Proposed laser propulsion systems would use negative temperature to accelerate spacecraft. Light sails pushed by population-inverted photons. The impossible might make interstellar travel possible. Astronomical observation. Adaptive optics uses laser-guide stars to correct atmospheric distortion. Telescopes employ negative temperature to see clearly. The impossible reveals the cosmic. SETI researchers consider negative temperature signatures as techno-signatures. Laser communication from alien civilizations would require population inversion. The impossible might be universal sign of intelligence. Optical SETI searches for laser pulses from distant stars. Any detected signal would indicate negative temperature technology. First contact might come through impossible physics. Some propose that advanced civilizations might use negative temperature for stellar engineering, using laser arrays, interstellar communication networks. Computational, megastructures, energy harvesting from black holes. The Fermi paradox. Why we see no aliens despite probable existence might involve negative temperature. Perhaps civilizations become detectable only after discovering population inversion. We've been technologically visible only since inventing lasers. Negative temperature enables personalized treatment. Photodynamic therapy. Light-activated drugs target specific cells. Population inversion. Creates precise wavelengths that activate medications exactly where needed. The impossible enables targeted possible healing. Laser immunotherapy. Immune responses triggered by specific laser wavelengths. Negative temperature stimulates precise biological responses. Population inversion becomes immune activation. Optical biopsy. Laser spectroscopy identifies cancerous tissue without cutting. Negative temperature reveals disease through light alone. The impossible makes invasive procedures unnecessary. Neural stimulation. Optogenetics uses laser light to control genetically modified neurons. Negative temperature enables precise brain stimulation. Thoughts triggered by impossible physics. Medical diagnosis transformed by negative temperature. Flow cytometry. Laser-based cell sorting uses multiple negative temperature sources. Individual cells analyzed at thousands per second. Population inversion. Indemil's population analysis. Confocal microscopy. Living tissue imaged in 3D using laser scanning. Negative temperature reveals cellular structure. The impossible makes the microscopic visible. Raman spectroscopy. Molecular fingerprints identified using laser scattering. Disease detected through vibrational signatures. Negative temperature becomes diagnostic tool. Optical coherence. Tomography. Tissue imaged using laser interferometry. Retinal diseases diagnosed without contact. The impossible enables non-invasive examination. Negative temperature teaches us to transcend binary oppositions. Hot-cold becomes a spectrum including hotter than infinite. Possible-impossible becomes a negotiable boundary. Order-disorder becomes bidirectional. Energy-centropy becomes exchangeable. This transcendence applies beyond physics. Success-failure becomes learning opportunity. Problem-solution becomes creative tension. Question-censure becomes ongoing dialogue. Self-other becomes interconnected system. Negative temperature models non-binary thinking. Just as temperature isn't simply hot or cold, reality isn't simply this or that. The impossible teaches us that categories are constructs, useful but limited. Living with negative temperature means living with productive paradox. Accepting contradiction. Negative temperature is simultaneously coldest and hottest. Accepting this paradox, without resolution, teaches intellectual flexibility, embracing confusion. The initial confusion about negative temperature is necessary for understanding. Confusion becomes doorway, not barrier. Seeking impossibility. Where common sense fails, discovery awaits. The impossible signals opportunity for breakthrough. Questioning absolutes. Absolute zero isn't absolute. No limit is truly limiting. Every boundary might be permeable. This paradox wisdom applies to life. Weakness can be strength. Loss can be gain. Ending can be beginning. Impossibility can be inevitable. Negative temperature raises ethical questions. Access and equity. Laser technology depends on negative temperature. Should impossible physics be universally accessible? How do we ensure equitable distribution of impossibility? Environmental impact. Creating negative temperature requires energy. How do we balance impossible physics with environmental responsibility? Military applications. Laser weapons use negative temperature. How do we prevent impossible physics from enabling possible destruction? Enhancement versus treatment. Medical lasers can treat disease or enhance appearance. Where do we draw lines with impossible physics? Information and privacy. Quantum cryptography. Using negative temperature could ensure perfect privacy or enable perfect surveillance. How do we navigate impossible security? These ethical dimensions show negative temperature isn't just scientific curiosity, but social responsibility. The impossible has moral implications. Years after first encountering negative temperature, I still marvel at its implications. Each day brings new appreciation for this impossible reality. Morning meditation. I contemplate population inversion as metaphor for consciousness. Perhaps awareness itself involves negative temperature. Thoughts organizing spontaneously. Consciousness emerging from thermodynamic impossibility. Teaching moments. Every confused student reminds me of my own initial bewilderment. Their journey from impossibility to understanding mirrors humanity's scientific progress. Research insights. Each experiment reveals new facets of negative temperature. The impossible keeps surprising. Paradox keeps producing insights. Daily wonder. Using a laser pointer still amazes me. I hold impossible physics in my hand, wielding paradox casually. Negative temperature has fundamentally altered how I see reality. Limits are provisional. Every absolute might have exceptions. Every impossibility might be misunderstanding. Paradoxes are productive. Where logic fails, truth might hide. Contradiction can reveal rather than conceal. Understanding evolves. Today's impossibility is tomorrow's technology. Knowledge is journey, not destination. Wonder is warranted. Reality exceeds imagination. To mystery is fundamental feature, not bug. Participation matters. We don't just observe reality, we participate in its creation. Our understanding shapes what's possible. This worldview extends beyond physics to all aspects of life. Relationships have negative temperature moments. Adding energy creates order. Creativity involves population inversion. Ideas organizing spontaneously. Growth requires accepting impossibility before achieving possibility. My students now grow up with negative temperature as fact. For them, the impossible is already possible. Their challenge is maintaining wonder at the paradox while using it practically. So I tell them, you inherit a world where impossible physics is infrastructure. Your smartphones use negative temperature. Your internet depends on it. But don't let familiarity breed complacency. The impossible remains impossible even when it's everyday. Their projects explore new impossibilities. Can consciousness be described thermodynamically? Do social systems exhibit negative temperature? Can economic models use population inversion? Does evolution involve negative temperature transitions? They're not content with using impossible physics. They want to find new impossibilities. Each generation pushes further into paradox, deeper into productive confusion. The 2030s will likely see medical breakthroughs, diseases cured using negative temperature therapies, cancer treated with precision impossible today, neural conditions addressed through population inversion, quantum revolution, quantum computers using negative temperature achieving advantage, impossible physics enabling impossible computation, problems unsolvable today, becoming routine, energy transformation, new energy systems using negative temperature, impossible efficiency achieved through population inversion, climate change addressed through paradoxical physics, space expansion, Mars colonies using negative temperature technology, asteroid mining with laser systems, impossible physics enabling possible expansion, social evolution, society reorganized around negative temperature capabilities, impossible becoming infrastructure, paradox becoming planning principle. By 2124, negative temperature might enable biological engineering, life forms designed with negative temperature metabolism, organisms that decrease entropy while living, impossible biology becoming possible, consciousness technology, artificial consciousness using negative temperature, machines that think through population inversion, impossible minds becoming possible, cosmic engineering, stellar manipulation using negative temperature, Dyson spheres powered by population inversion, impossible megastructures becoming possible, reality manipulation, direct control of thermodynamic properties, creating and destroying negative temperature, at will, impossible physics becoming programmable, temporal technology, time manipulation through negative temperature, entropy reversal in controlled regions, impossible chronology becoming possible. In 1,000 years, negative temperature might be fundamental tool, as basic as fire or electricity today. Children learning population inversion before multiplication, impossible physics becoming elementary, civilizational foundation, entire civilizations based on negative temperature, societies organized around population inversion, impossible becoming inevitable, cosmic principle, negative temperature recognized as fundamental cosmic principle, universe understood through impossible physics, paradox becoming paradigm, evolutionary driver, life evolving to use negative temperature naturally, biology, incorporating population inversion, impossible becoming biological, reality basis, reality itself understood as negative temperature phenomenon, everything emerging from population inversion, impossible becoming everything. Beyond physics, beyond technology, negative temperature teaches profound lessons. Reality is richer than appearance. What seems impossible might be essential. Surface understanding hides deeper truth. Categories are constructs. Hot, cold, possible, impossible, order, disorder, all human constructs imposed on richer reality. Paradox is productive. Contradiction drives discovery. Confusion precedes comprehension. Understanding evolves. Knowledge is provisional. Today's truth is tomorrow's approximation. Wonder is appropriate. Reality exceeds imagination. Mystery is permanent feature. We participate in possibility. Our understanding shapes what's possible. Observation creates reality. The impossible is everywhere. We're surrounded by paradox. We use impossibility daily. Mystery is practical. The unexplained becomes technology. Paradox becomes product. These lessons apply universally. Every field has its negative temperatures, impossibilities that become essential. Every life has population inversions, moments when energy creates order. From cosmic perspective, negative temperature might be universal feature. Every advanced civilization discovers negative temperature. It's not human discovery, but universal inevitability. Evolutionary milestone. Species that master negative temperature survive. Population inversion enables cosmic expansion. Reality's nature. The universe itself might be negative temperature system. Big Bang might be population inversion. Everything might be impossible. Consciousness, requirement. Awareness might require negative temperature. Mind might be population inversion. Consciousness might be impossible. Physics. This cosmic perspective humbles and inspires. We're not just discovering physics, but participating in cosmic evolution. Our mastery of negative temperature might be species transformation. Impossible physics, enabling impossible future. As we conclude, I extend personal invitation. Question your impossibles. What do you consider impossible? Might it be misunderstanding? Embrace productive confusion. Where are you confused? Might confusion signal opportunity? Seek paradoxes. What contradictions surround you? Might they hide truth? Create inversions. Where can you add energy to create order? Where can you achieve population inversion? Live impossibly. How can you embody negative temperature? How can you make impossible real? This isn't just intellectual exercise, but life philosophy. Negative temperature shows that living impossibly isn't fantasy but physics. We can achieve population inversion, personally, socially, spiritually. We quote Ver traveled from classical thermodynamics through quantum paradox to cosmic possibility. We've seen how negative temperature violates common sense, yet enables common technology. Through we've discovered that impossible physics surrounds us, supports us, connects us. The journey revealed that absolute zero isn't absolute infinity, isn't the limit. Impossible is possible. Paradox is practical. Mystery is mundane. But more than facts, we've discovered philosophy. Negative temperature isn't just physics phenomenon, but metaphor for human potential. We too can achieve impossible states, create order from energy, exist in paradox productively. If you've journeyed with attention, you've achieved intellectual population inversion. Your mental state has shifted. Ideas that seemed impossible now seem inevitable. Paradoxes that seemed problematic now seem productive. This transformation is negative temperature's gift. Not just knowledge, but new way of knowing. Not just facts, but new way of thinking. Not just information, but transformation. You now carry impossible physics in your understanding. You know that your laser pointer violates common sense. Your internet depends on paradox. Your medical care uses impossibility. Your future requires negative temperature. But more importantly, you know that impossibility is invitation. That paradox is possibility. That confusion is doorway. That wonder is warranted. Despite all we've learned, mystery remains. We know how to create negative temperature, how to use it, how to describe it mathematically, but we don't know why it exists, what it means ultimately, how deep the paradox goes. To this continuing mystery is gift, not failure. It means discovery continues. Wonder remains justified. Understanding keeps evolving. Mystery is permanent. The impossible stays impossible, even when possible. Negative temperature reminds us that reality is inexhaustible. Every answer reveals new questions. Every understanding opens new mystery. Every possibility suggests new impossibility. As we take final temperature reading, we find ourselves in unique state. We understand negative temperature intellectually, yet it remains mysterious experientially. Springs, we use it practically, yet it stays paradoxical conceptually. We've mastered it technologically, yet it masters us philosophically. This is appropriate final state, suspended between knowing and not knowing, between possible and impossible, between understanding and mystery. We exist at intellectual negative temperature, population inverted, energy creating order, entropy decreasing locally, while increasing universally. You now join the ranks of those who know the impossible is real, who understand that below absolute zero lies not nothing but everything, who realize that beyond infinite heat lies hotter still, who grasp that paradox is not problem but portal. Negative temperature will remain impossible even as it becomes increasingly essential. Future generations will use it more casually, yet the paradox will persist. Technology will advance, but mystery will remain. This eternal impossibility is negative temperature's deepest teaching. Some things remain wonderful, no matter how familiar. Some paradoxes stay productive, no matter how explored. Some mysteries persist, no matter how investigated. You now carry this eternal impossibility within you. Every time you use laser technology, you wield paradox. Every time you benefit from fiber optics, you depend on impossibility. Every time you receive medical laser treatment, you're healed by paradox. But more than using impossible physics, you now think impossibly. You've achieved mental population inversion. Your thoughts favor higher energy states. Your understanding embraces paradox. Your worldview includes impossibility as possibility. Temperature began as simple concept. Hot and cold. Up and down on Mercury column. It seemed straightforward, intuitive, absolute zero, appeared to be ultimate limit, insurmountable barrier, end of possibility. But nature laughed at our limitations. Reality revealed richness we never imagined. The impossible not only became possible, but necessary. The paradox not only resolved, but became productive. The mystery not only persisted, but became practical. Negative temperature stands as monument to nature's creativity, reality's richness, possibility's extent. It reminds us that every limit might hide passage, every impossibility might mask opportunity, every paradox might produce breakthrough, every confusion might precede comprehension, every mystery might become technology. As you return to world of positive temperature, remember your excursion into impossibility. Remember that you live surrounded by paradox made practical. Remember that civilization depends on impossible physics. Remember that you yourself might operate at negative temperature. The thermometer has spoken its impossible truth. The measurement reads below absolute zero. The paradox has become paradigm. The impossible has become essential. Welcome to reality, where negative temperature is real, where impossible is infrastructure, where paradox is practical, where mystery is mundane yet remains mysterious. Your temperature has been taken. The reading is impossible, and that impossibility illuminates everything. The observation is complete. The population is inverted. The impossible is achieved. Negative temperature is real. You understand it. You use it. You embody it. The paradox persists. The mystery remains. The wonder continues. Below absolute zero, beyond infinite heat, through impossible physics, into impossible future. The journey ends where it began, with wonder at reality's impossible possibility. Temperature, negative, status, impossible, reality, confirmed. Welcome to the impossible world you've always lived in, but now consciously inhabit.